Welcome to our quantum deep dive. We all see it. Artificial intelligence is exploding, getting smarter and more capable every single day. But behind the curtain, it's also creating a massive hidden problem.
That's exactly right. Today, we're digging into an essay by Jörg Owe Schneppat to explore how the truly strange world of quantum mechanics might be the only way to solve AI's huge energy crisis and, just maybe, unlock the next level of intelligence itself.
So here's our game plan. We'll start by pulling back the curtain on that secret crisis plaguing today's AI. Then, we'll look at the limits of the computers they run on before diving headfirst into the quantum solution, the very real challenges it faces, and what this all could mean for the future.
Okay, let's get right into it. We're all getting pretty used to what modern AI can do, right? This isn't just science fiction anymore. It's becoming a real part of our lives, fast.
It can write that tricky email for you, create these incredible images from just a few words. It can even write computer code. It feels almost like magic, and it's totally changing the game for how we use technology. But yeah, all this magic has a cost, and it happens behind the scenes where we don't see it. And that price is, well, it's staggering. We're not just talking about money, we're talking about energy, resources, and even the fundamental limits of the AI models themselves.
You see, today's AI models are running smack into a wall, a fundamental limit. And it's not about clever software, it's about the hardware, the classical computers they run on. They're starting to seriously creak under the strain of these enormous demands.
We're really starting to see this law of diminishing returns kick in. To make these models just a little bit smarter, we have to throw exponentially more power at them. And even then, they still struggle with some pretty basic stuff. They forget what you were talking about 5 minutes ago. They literally make things up. Researchers call these hallucinations. And of course, they can end up just repeating the worst biases from the data they were trained on.
And that energy consumption, just to put it in perspective for you, training one of these big models just one time is estimated to pump out 550 tons of carbon dioxide. That is the same as the entire lifetime emissions of 5 cars. You just can't keep scaling that up. It's not sustainable.
So, to get over this wall, researchers are looking somewhere completely different. They're leaving the world of classical computing behind and entering the quantum realm, a bizarre landscape first mapped out by names you've probably heard, like Planck, Einstein, and Schrödinger.
And this really gets to the heart of it. A classical computer bit is super simple. It's a light switch. It's either off, a 0, or it's on, a 1. That's it. But a quantum bit, or a qubit, is where things get weird. Thanks to quantum mechanics, it can be both 0 and 1 at the exact same time. It exists in this whole spectrum of possibilities.
This mind-bending property is called superposition, and because one qubit can hold multiple values, a quantum computer with n qubits can process 2 to the power of n states all at once. We're not talking about a small speed boost here. This is an exponential, explosive leap in processing power.
And just when you think you've got your head around that, it gets even stranger with something called entanglement. This is where 2 or more qubits become linked in this deep, fundamental way. Their fates are tied together, no matter if they're next to each other or on opposite sides of the galaxy. You measure one, and you instantly know the state of the other. It's so weird, it prompted Einstein himself to famously call it spooky action at a distance.
Okay. So we've got this weird new quantum toolkit with superposition and entanglement. It's fascinating stuff. But how on earth does this help us build better, more efficient AIs that can understand language?
Well, it turns out these quantum solutions map perfectly to the classical problems we talked about. That massive energy bill? Quantum parallelism, with its ability to check millions of possibilities at once, tackles that head-on. The AI's bad memory. Entanglement can create those spooky links between related words, even if they're pages apart in a document, giving the AI a much deeper sense of context. And for the training process itself, a technique called quantum annealing can find the best way to set up the model way more efficiently.
Now, before we get too carried away and declare the problem solved, we have to have a reality check. Building a useful quantum computer, one that can actually do all this, is honestly one of the greatest engineering challenges humanity has ever faced. Here's the thing. The quantum world is unbelievably fragile. These special states, like superposition and entanglement, are so delicate. The slightest vibration, the tiniest change in temperature from our normal, noisy world can destroy them. So protecting them is just a monumental task.
The number one enemy here is something called decoherence. It's a fancy word for when noise from the environment just causes the qubit to collapse and lose its quantum magic, turning it back into a boring old classical bit. The best solution we have is quantum error correction, which basically means you have to use a whole bunch of physical qubits just to create one stable, reliable, logical qubit. It's a huge overhead.
So this gives you a rough idea of the roadmap. Right now we are in what they call the NISQ era. That stands for Noisy Intermediate Scale Quantum. Think of them as early, error-prone prototypes. The next logical step is probably hybrid systems, where a classical computer does most of the work, but hands off the really hard problems to a quantum chip. Looking further out, a lot of projections are pointing to around 2030 for when we might see the first truly practical, fault-tolerant quantum computers.
But let's say we do it. Let's say we overcome all these insane hurdles. What does this new frontier of intelligence actually look like? What could it do?
Oh, the possibilities are just transformative. We're talking about flawless, real-time translation that doesn't just swap words, but truly understands nuance and culture. An AI that could be hyper-creative, generating art and stories with real depth. Or imagine a tool that could scan millions of medical records to help a doctor with a diagnosis, or sift through every legal precedent instantly. It's a whole new ballgame.
Of course, with great power comes great risk. A fully fledged quantum computer running an algorithm like Shor's algorithm could, in theory, break most of the encryption that protects our entire digital world. Our bank accounts, our private messages, government secrets, everything. This threat has already kicked off a massive new arms race in cybersecurity.
And that brings us to maybe the deepest, most profound question of all. A quantum AI wouldn't just be smarter in a way we recognize. Its entire thought process is based on the laws of quantum mechanics. Its logic is born from superposition and entanglement. So how would we even communicate with an intelligence that perceives reality in a way that is so fundamentally different from our own?
Thank you for joining us. As we've seen from Jorgo Vishnepat's work, this is way more than just a simple upgrade for AI. It really is a potential paradigm shift, not just in computation, but maybe in our understanding of intelligence itself. To read the original essay and dive even deeper into all these ideas, we definitely recommend you visit schnepa.de. Goodbye!
Schnepat.de is a private project by Jorgo Schnepat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.